And we're going to break it down step by step.
So here's our setup. It's honestly a bit of a mathematical crime scene. We've got this blank Venn diagram, two intersecting circles labeled F for football and T for tennis, an unknown variable x just sitting right there in the middle, and the number 8 hanging out in the corner. Our whole goal today is to figure out the exact number of students in each specific subset. Basically, we need to unmask that x, turn it into a real number, and fill in the rest of the blanks.
Section 1. Gathering our clues. Let's find the facts. Like any good detective story, before we can find our culprit X, we need to isolate the hard facts. Let's just lay out the evidence exactly as it was given to us. First, we've got our universe, our absolute hard limit of 28 students total in the class. Next, we know 15 students play football. We've got 12 students who play tennis. And finally, 8 students who play neither sport. They're the ones represented by that 8 outside the circles. You know, they're probably just chilling on the bleachers reading a book or something. But anyway, that is our raw data. Which brings us to Section 2, the overlap dilemma. This is where things get weird.
Let's just do some really basic instinctual math. If we take those raw categories and just add them straight up, the 15 football players plus the 12 tennis players plus the 8 kids on the bleachers, we get a total of 35.
Okay, hold on a second. I really want to pause here because this is the absolute crux of the entire mystery. How on earth can our subgroups add up to 35 when the entire universe of our class, which we just established as a hard fact, is strictly capped at 28? We literally have 7 phantom students floating around in our math. Where did they even come from?
Well, the answer lies in a classic analytical trap. The reason our numbers are completely out of whack is due to a phenomenon called double counting. This is basically the error of counting overlapping items in a set twice, which creates this artificially high total. So in our class, the kids who play both sports are being counted once when we tally up the 15 football players, and then a second time when we tally up the 12 tennis players. They're inflating our total because, well, they literally have a foot in both circles.
All right, Section 3, solving for x. Let's unmask this variable. So this extra bloat we're seeing is exactly what our mystery variable x represents. And cutting through the noise is actually pretty straightforward once you see it. Step 1, we find that total sum of our raw categories, which we did. 15 plus 12 plus 8 gave us that inflated number of 35. Step 2, we subtract reality. We take our inflated 35 and subtract the actual class size limit of 28. That leaves us with exactly 7. And step 3 tells us that this difference is our overlap. Just by taking the raw total and subtracting the reality, we've perfectly isolated the exact number of students who were double counted.
Boom. There it is. This brilliantly illustrates that our unknown variable x, the kids playing both football and tennis right in that center intersection, has to be 7. We've solved the core of the puzzle, right there. X is 7.
But we are not done yet. Section 4, completing the picture. Let's fill in the rest of those blanks.
We need to take this golden key of 7 and use it to unlock the true values of the other sections. And guys, this is honestly where so many people get tripped up on these kinds of problems. Because look, there is a massive difference between the 15 students who play football in total and the subset of students who exclusively play football and absolutely nothing else. If we know 15 kids play football total, but we now know 7 of those kids also play tennis, well, we have to subtract them to find our purists. 15 minus our overlap of 7 equals 8. So exactly 8 students play only football.
And we just apply that exact same logic to tennis to get our final missing piece. We take the 12 total tennis players from our first set of clues, we subtract the 7 multisport athletes who play both, and we are left with exactly 5 students who play only tennis. And just like that, we have completely isolated every single specific subset.
Let's double-check the math just to be absolutely sure.
When we lay out these pure, isolated subsets, we can finally add them up without any risk of double counting. We've got the 8 who only play football, plus the 7 who play both, plus the 5 who only play tennis, plus the 8 on the bleachers who play neither. So 8 plus 7 is 15, plus 5 is 20, plus 8 is 28. It adds up to a perfect 28 students. The math, finally, beautifully matches our reality.
It's honestly super satisfying when it all just clicks into place visually. Every single one of our 28 students now has a specific logical home. There's no more ambiguity, and way more importantly, there's no double counting throwing off our big picture. We took what was essentially a jumbled set of overlapping clues and distilled the whole thing down into perfectly clean, precise data points. As we wrap up this explainer, I want you to take a step back and think about how this kind of visual logic applies way beyond a classroom or a math test. Seriously, think about your monthly budget or your calendar or how you might be looking at data at work. Whenever overlapping categories aren't properly separated, it instantly creates a distorted reality exactly like our phantom 35 students. So ask yourself, where else are hidden overlaps distorting your bigger picture? If you keep an eye out for those hidden X variables out there in the real world, you'll always have a much more accurate read on what's actually going on.